Welcome! Today, we'll dive into LeetCode problem number 1617, count subtrees with max distance between cities. This fascinating problem challenges us to analyze subtrees and calculate their maximum distances. Let's explore the problem, break it into manageable steps, and discover an optimal solution. Stay tuned! In this problem, you are tasked with analyzing a network of cities. Specifically, you're given an integer n, which represents the number of cities labeled from 1 to n, and an edges array, where each element, u_i, represents a bidirectional road between two cities. The goal is to explore all possible subtrees within this network. A subtree is a subset of cities and roads that forms a tree, meaning it is connected and does not contain cycles. The distance between two cities is defined as the number of roads that need to be traversed to travel between them. The diameter of a tree is the maximum distance between any two cities within that tree. Using this information, your task is to return an array answer of size n1. Each element answer, I, represents the count of subtrees where the diameter is equal to I plus 1. To clarify this further, let's look at an example. Suppose n equals 4 and the edges array is 1, 2, 2, 3, 2, 4. Here, you are working with 4 cities connected by 3 roads. The output is 3, 4, 0. This means there are 3 subtrees with a diameter of 1, for subtrees with a diameter of 2, and no subtrees with a diameter of 3. Let's break this down. Subtrees with a diameter of 1 include 1 to 2, 2 to 3, and 2 to 4, each involving a single edge. Subtrees with a diameter of 2 include 1, 2, 3, 1, 2, 4, 2, 3, 4, and 3, 2, 4, which are slightly larger. Finally, there are no subtrees where the maximum distance between two cities is 3 in this particular configuration. Now, consider another example where n equals 3 and edges equals 1, 2, 2, 3. Here, the output is 2, 1. This indicates that there are 2 subtrees with a diameter of 1 and 1 subtree with a diameter of 2. Specifically, the subtrees 1 to 2 and 2 to 3 each have a diameter of 1, while the subtree 1 to 3, which includes all 3 cities, has a diameter of 2. These examples illustrate how to calculate the diameter for every possible subtree and group the counts accordingly. To solve this problem, it's important to understand the constraints. First, the number of cities n ranges from 2 to 15, meaning the problem size is small enough to allow brute force enumeration of all possible subtrees. The edges array will always have exactly n1 elements, ensuring the graph is connected. Each edge connects 2 distinct cities labeled from 1 to n. Some edge cases to consider include the minimum case where n equals 2, resulting in only one subtree with a diameter of 1, and more complex structures like fully balanced trees or skewed trees. In balanced trees, diameters are distributed uniformly, while in skewed trees, the maximum diameter can reach n1. With these constraints and edge cases in mind, you can systematically explore all subtrees and calculate their diameters to produce the required output. To begin solving this problem, we need to compute the number of subtrees for each possible maximum distance. A subtree is any connected subset of cities, and the maximum distance is defined as the largest distance between any 2 nodes within that subtree. At first glance, a brute force approach might seem feasible. This would involve generating all possible subsets of cities and verifying whether each subset forms a connected subtree. For each valid subtree, we would calculate the maximum distance between all pairs of nodes using either breadth-first search or depth-first search. However, there are 2 major challenges with this method. First, the number of subsets grows exponentially with the number of nodes, specifically 2n1 subsets of edges. Second, verifying connectivity and calculating distances for each subset becomes computationally expensive as the graph size increases. Combining these factors results in a total time complexity of n² 2 to the power of n, which quickly becomes infeasible for graphs with more than 16 nodes. This illustrates the need for a more efficient approach. To address the inefficiencies of the brute force method, we turn to an optimized approach that leverages bit masking and pre-computed distances. The first step in this strategy is to pre-compute the shortest distances between all pairs of nodes using a method like BFS or Floyd-Warshall. This pre-computation ensures that we don't have to repeatedly calculate distances during subtree evaluation. Once we have these distances, we can represent all possible subsets of nodes as bitmasks, which provide a compact way to enumerate subsets efficiently. For each subset, we then verify connectivity using BFS or DFS. If the subset forms a connected subtree, we calculate the maximum distance using the pre-computed pairwise distances. Finally, we maintain a count array to store the number of subtrees corresponding to each maximum distance. This optimized approach systematically reduces redundant calculations and organizes the problem into manageable steps. There are several key insights that make this optimized approach effective. First, by using bitmasking, we can enumerate subsets in a compact and systematic manner. Second, pre-computing pairwise distances eliminates the need to repeatedly calculate distances for every subset, significantly improving efficiency. In terms of complexity, the pre-computation step runs in O, n cubed, while the enumeration of subtrees using bitmasking and connectivity checks takes O, 2 to the power of n asterisk n squared. This results in a total time complexity of O, 2 to the power of n asterisk n squared, which is feasible for graphs with up to 15 nodes. These improvements make this approach a practical solution within the constraints of the problem. The chosen strategy combines the efficiency of pre-computation with the systematic enumeration of subsets via bitmasking. The intuition behind this approach is that pre-computing pairwise distances allows us to reuse this information across all subsets, avoiding redundant calculations. This insight was a critical breakthrough in reducing the overall complexity. By representing subsets as bitmasks, we streamline both the enumeration and the connectivity verification processes. However, there are trade-offs to consider. Pre-computing distances requires O, n squared, memory, which is acceptable for small graphs but could become limiting for larger inputs. Additionally, the bitmask-based method, while efficient for n less than or equal to 15, cannot scale to significantly larger graphs due to the exponential growth in the number of subsets. Overall, this strategy achieves an optimal balance between time and space complexity for the given constraints of the problem. The implementation of this strategy involves 4 main steps. First, we use BFS or the Floyd-Warshall algorithm to pre-compute pairwise distances between all nodes. Second, we use bitmasking to enumerate all possible subsets of nodes. For each subset, we validate whether it forms a connected subtree and, if it does, calculate the maximum distance using the pre-computed distances. Finally, we maintain a frequency array to aggregate the results, storing the count of subtrees for each maximum distance. From a complexity perspective, the time complexity is O, 2 to the power of n asterisk n squared, driven primarily by the subset enumeration and connectivity checks, while the space complexity is O, n squared, for storing the pre-computed distances. These steps ensure that the algorithm is both efficient and well-suited for the problem's constraints. In this problem, we're tasked with counting the number of subtrees in a graph where the maximum distance between any 2 nodes matches a specific value. The graph consists of cities represented as nodes, connected by bidirectional edges. A subtree here is any connected subgraph of the graph, and we need to compute the maximum distance within each subtree. This means finding the farthest 2 nodes in each valid subtree and determining how many subtrees exist for each possible maximum distance. The constraints are key. It's a connected graph with up to 15 nodes, which means the tree is relatively small. This allows us to explore all subsets of nodes while ensuring we compute results efficiently. The goal is to solve this for all possible maximum distances in every subtree, making it a combinatorial and graph traversal challenge. To solve this problem, we follow a structured approach. First, we represent the graph using an adjacency matrix or adjacency list. For an adjacency matrix, we create an nxn grid where each entry indicates whether an edge exists between 2 nodes. This representation is useful for quickly querying edge connections. Next, we generate all possible subtrees of the graph. This involves using bitmasking to enumerate all non-empty subsets of nodes, which amounts to 2n 1 subsets for n nodes. For each subset, we check if it forms a connected graph. This is done by using a traversal algorithm like BFS or DFS to verify that all nodes in the subset are reachable from a starting node. If a subset is connected, it qualifies as a valid subtree. This step ensures we only consider meaningful subgraphs for further calculations. Once we have valid subtrees, the next step is to calculate the maximum distance within each subtree. For this, we compute the shortest paths between all pairs of nodes in the subtree using a method like BFS or Floyd-Warshall. From these shortest paths, we identify the longest shortest path, which represents the maximum distance for that subtree. Now, we maintain a count array, where each index corresponds to a specific maximum distance, and the value at that index indicates how many subtrees have that distance. For each valid subtree, we increment the respective count for its maximum distance. Several key insights make this approach efficient. The small input size of n equals 15 makes it feasible to explore all subsets of nodes. Also, ensuring connectivity is critical to avoid invalid subtrees, and pre-computing shortest paths can significantly speed up distance calculations. The undirected nature of the graph further simplifies traversal and distance computations. The overall complexity of this solution is determined by the various steps. Generating all subsets of nodes takes O(2 to the power of n), and for each subset, checking connectivity requires O(n²), using BFS or DFS. Calculating the maximum distance within a subtree, using Floyd-Warshall or BFS for all pairs, takes O(n³). Combining these, the total complexity is O(2 to the power of n*n³), which is manageable given the constraint of n equals 15. There are a few edge cases to handle carefully. For the minimum case of n equals 2, there's only one valid subtree, and the maximum distance equals the single edge length. Subsets that aren't fully connected should be ignored, and it's important to count subtrees accurately when multiple subtrees share the same maximum distance. Lastly, since the graph is symmetric with bidirectional edges, ensuring correct handling of edge symmetry is crucial for both traversal and distance calculations. Here, we start by importing the combinations function from the itertools module, which will help us later in generating subsets of nodes. Next, we define the solution class and the method count subgraphs for each diameter, which takes two parameters, n, the number of cities, and edges, the connections between them. Inside the method, we first construct an adjacency list called graph to represent the tree structure. Each node is mapped to a list of its directly connected neighbors. This adjacency list will allow us to efficiently traverse the graph during later computations. We then define a helper function called BFS_max_distance, which uses breadth-first search to calculate the maximum distance between a given starting node and all other nodes in a specific subset. The function initializes a visited dictionary to keep track of nodes that have already been explored. A queue is used to manage the BFS traversal, where each entry contains a node and its distance from the starting point. As we explore the graph, we update the max_dist variable to track the farthest distance encountered. This function will be central to determining the diameter of a subtree formed by a subset of nodes. Now, we introduce another helper function called is_connected, which checks if a given subset of nodes forms a connected subtree. This function uses depth-first search to traverse the nodes in the subset. Starting from any node in the subset, we recursively visit all reachable nodes, marking them as visited. If all nodes in the subset are visited by the end of the DFS, the subset is connected, and we return true. Otherwise, it is not a valid subtree, and we return false. Moving forward, we initialize a result list with n1 zeros, where each index represents the count of subtrees with a specific diameter. We then iterate through all possible subsets of nodes, starting with subsets of size 2, since a single node cannot form a subtree with a measurable diameter. For each subset, we first check if it is connected using the is_connected function. If it is, we calculate the maximum distance or diameter within the subset using the BFS_max_distance function. This involves iterating over all nodes in the subset and finding the farthest distance from each one. If the diameter is within the range of valid values, specifically between 1 and n1, we proceed to record it. Finally, we use the diameter value to update the result list. Since the diameter is 1 based but the result list is 0 indexed, we adjust the index by subtracting 1 and then increment the corresponding value. This ensures that we count the number of subtrees for each possible diameter correctly. Once all subsets have been processed, the result list contains the desired counts for diameters ranging from 1 to n1. We then return this list as the output of the function. This concludes the implementation, where we utilized graph traversal techniques and combinatorics to efficiently solve the problem of counting subtrees based on their maximum distance. Here, we begin by creating the adjacency list to represent the graph. This is done using a hash map where each node maps to a list of its neighbors. We initialize the graph so that every node from 1 to n has an empty list, and then populate it by iterating through the given edges and adding the connections for both directions. Next, we define a helper function, BFSMaxDistance, which calculates the maximum distance within a subset of nodes using breadth-first search. Starting from a given node, we use a queue to explore the graph level by level. For each node, we track its distance from the starting node and update the maximum distance encountered. We also maintain a visited set to ensure we don't revisit nodes, which prevents infinite loops and ensures correctness. This BFS function gives us the farthest distance within the connected subset of nodes. The next helper function, isConnected, checks whether a given subset of nodes forms a connected subgraph. To do this, we use a depth-first search, or DFS, which starts from any node in the subset and explores all reachable nodes. The DFS function recursively visits neighbors that are part of the subset and haven't been visited yet. After the DFS completes, we compare the size of the visited set to the size of the subset. If all nodes in the subset have been visited, the subset is connected, otherwise, it's not. These two helper functions, BFSMaxDistance and isConnected, form the foundation for solving the problem by allowing us to evaluate properties of subsets of nodes. Now, we define the result array, which will store the count of subgraphs for each possible diameter. To compute this, we iterate through all subsets of nodes, starting with subsets of size 2 up to n. For each subset, we first generate all combinations of nodes of that size using the generateSubsets function. Then, for each subset, we check if it's connected using the isConnected helper function. If the subset is connected, we calculate its maximum diameter by running BFSMaxDistance for every node in the subset and keeping track of the largest distance. If this diameter is valid, that is, it lies between 1 and n1, we increment the corresponding index in the result array. This ensures that we count all valid subgraphs for each possible diameter. Finally, the generateSubsets function is responsible for generating all possible subsets of a specific size k from the n nodes. This is done recursively. The generate function adds nodes one by one, starting from the given index, and stops when the current subset reaches the desired size. Once a valid subset is formed, it's added to the list of subsets. After adding the current node, we backtrack by removing it and try the next possibility. This process ensures that we explore all combinations of nodes systematically. Together, these functions complete the solution, and the result array is returned as the final output, representing the count of subgraphs for each possible diameter. To solve this problem, we start by constructing the graph using an adjacency list. The edges provided define the connections between nodes, so for each edge, we update the adjacency list to reflect the connections in both directions. For example, edge 1, 2 tells us that node 1 is connected to node 2, and vice versa. Similarly, edge 2, 3 adds connections between nodes 2 and 3, and edge 2, 4 adds connections between nodes 2 and 4. After processing all the edges, the final adjacency list shows how the nodes are interconnected. Once the graph is built, we move on to iterating over all subsets of nodes, starting from subsets of size 2 because a subtree must have at least 2 nodes. By generating these subsets, we prepare to check which of them form valid subtrees and calculate their maximum distances. Now, let's analyze the subsets. For the subset 1, 2, we first check if it forms a connected subtree. Using a depth-first search starting from node 1, we visit nodes 1 and 2, confirming that the subset is connected. Then, we calculate the maximum distance within this subset using breadth-first search. Starting from node 1, the farthest node is node 2, with a distance of 1. Since the maximum distance is 1, we update the result array at index 0, which corresponds to distances of 1, making the result 1, 0, 0. Similarly, for subset 2, 3, starting a DFS from node 2 shows that nodes 2 and 3 are connected. The BFS identifies the maximum distance as 1, so we update the result array again at index 0, giving us 2, 0, 0. For subset 1, 2, 3, we verify connectivity starting from node 1, visiting nodes 1, 2, and 3. The BFS shows the maximum distance is 2, measured from node 1 to node 3. We update the result array at index 1, resulting in 2, 1, 0. After updating the result for subset 1, 2, 3, we continue the process for all other possible subsets, performing the same steps of checking connectivity and calculating the maximum distances. By the end of this analysis for all subsets, the final result array for this example is 3, 2, 1. This means there are 3 subtrees with a maximum distance of 1, 2 subtrees with a maximum distance of 2, and 1 subtree with a maximum distance of 3. With this example complete, we move on to another case to further solidify our understanding of the solution. In this new example, we have 3 nodes connected by the edges 1, 2, and 2, 3. The first step, as before, is to construct the graph. Using the edges, we build the adjacency list, which represents the connections between nodes. Here, node 1 connects to node 2 connects to nodes 1 and 3, and node 3 connects back to node 2. This results in the adjacency list 1, 2, 2, 1, 3, 3, 2. With the graph built, we proceed to analyze the subsets. For subset 1, 2, a depth-first search starting at node 1 confirms that nodes 1 and 2 are connected. Using BFS, we calculate the maximum distance in this subset, which is 1, measured between node 1 and node 2. We update the result array for distances of 1, making it 1, 0. Next, for subset 2, 3, starting DFS at node 2 reveals that nodes 2 and 3 are connected. BFS again shows the maximum distance within this subset is 1, so we update the result array at index 0, yielding 2, 0. For subset 1, 2, 3, DFS starting at node 1 confirms connectivity, visiting nodes 1, 2, and 3. The BFS determines the maximum distance is 2, from node 1 to node 3. We update the result array at index 1, resulting in 2, 1. After processing all subsets, the final result for this example is 2, 1. This tells us that there are 2 subtrees with a maximum distance of 1 and 1 subtree with a maximum distance of 2. By systematically constructing the graph, iterating over subsets, checking connectivity, and calculating distances, we can solve this problem efficiently. This approach ensures that we correctly count the number of subtrees with each possible maximum distance for any given graph. To analyze the time complexity of our solution, let's start by breaking it down into its components. First, the algorithm iterates through all subsets of nodes in the graph. Since there are n nodes, the total number of subsets is approximately 2 to the power of n, as we consider all possible combinations of nodes with sizes ranging from 2 to n. Next, for each subset, we need to check if the nodes in the subset form a connected subtree. This operation uses a depth-first search, or DFS, and in the worst case, it takes n time for each subset. Finally, we compute the maximum distance between nodes within each subset using a breadth-first search, or BFS, which is performed from each node in the subset. The BFS computation requires n squared time in the worst case, as we could potentially perform BFS for all n nodes within the subset. Combining these steps gives us the foundational components of the time complexity. Now, combining all these operations, for each subset, we first check connectivity, which is n, and then calculate maximum distances using BFS, which is n squared. This results in a per subset time complexity of n squared. Since there are approximately 2 to the power of n subsets in total, the overall time complexity of the subset exploration becomes 2 to the power of n asterisk n squared. Additionally, we account for the one-time cost of constructing the adjacency list for the graph, which takes n plus e, where e is the number of edges. However, this pre-processing cost is negligible compared to the exponential growth in the subset exploration, so the dominant factor in the overall time complexity remains 2 to the power of n asterisk n squared. Turning to space complexity, the overall space usage is n plus e plus 2 to the power of n. Let's break this down. First, the graph representation, which we store as an adjacency list, requires n plus e space. This accounts for the nodes and edges in the graph. Second, the BFS operation uses a visited set and a queue, both of which require n space at most during execution. Third, subsets of nodes are generated dynamically during the iteration process. While there are 2 to the power of n subsets, they are not stored in memory all at once, so their contribution to space usage is managed efficiently. Finally, the result array, which stores the counts of subtrees for each possible diameter, has a fixed size of n. Combining these factors, the space complexity is dominated by the adjacency list and the temporary structures used during BFS and subset generation, resulting in n plus e plus 2 to the power of n. Comparing this solution to a brute force approach highlights the efficiency gained. A naive brute force method might explicitly compute all paths between every pair of nodes in every subset, which would lead to a much higher time complexity of 2 to the power of n asterisk n to the power of 4. This is because it would involve an additional iteration over all node pairs for each subset. In contrast, our solution avoids this inefficiency by leveraging BFS to compute distances within subsets, reducing the complexity to 2 to the power of n asterisk n cubed. We also observe how the graph structure impacts performance. In sparse graphs, many subsets are disconnected, allowing the connectivity check to quickly prune invalid subsets and minimize BFS calls, representing the best-case scenario. On the other hand, with dense graphs, most subsets are connected, requiring full BFS computations for all nodes in the subset, which corresponds to the worst-case complexity of 2 to the power of n asterisk n cubed. To summarize the reasoning behind the big O complexity, the exponential growth of subsets, at 2 to the power of n, is the primary driver of the time complexity. This is combined with the per-subset operations, where BFS computations for maximum distances contribute n squared, and connectivity checks add an additional n. Together, these factors multiply to form the overall time complexity of 2 to the power of n asterisk n cubed. For space complexity, the dominant factors are the graph representation in the adjacency list and the temporary structures used during BFS and subset generation. These components result in a total space complexity of n plus e plus 2 to the power of n, which balances the storage requirements for the graph, BFS operations, and the result array. This mathematical breakdown validates the efficiency and scalability of the solution within the constraints of the problem. When solving this problem, there are a few common mistakes to watch out for. First, misunderstanding what constitutes a valid subtree can lead to errors. A subtree must be a connected subset of cities, and all edges in the subset must be present. If you don't carefully validate this, you might count invalid subtrees or miss valid ones. Next, inefficient distance calculations can drastically increase runtime. If you're recalculating distances for every subtree, it can become computationally expensive, especially with larger inputs. To address this, pre-computing pairwise shortest paths using algorithms like Floyd-Warshall or BFS ensures distance lookups are quick and efficient. Lastly, failing to use bit masking for subset generation can create inefficiencies. While nested loops or recursion might seem intuitive, bit masking is much faster when enumerating subsets, particularly for smaller graphs with up to 15 cities. Another mistake is ignoring the symmetry in undirected graphs. Since edges like u, v, and v, u are the same, failing to normalize or account for this symmetry can lead to double counting or incorrect results. Always ensure that edges are treated bidirectionally and representations are consistent. Additionally, not pruning invalid subtrees early can waste significant computation time. For example, if a subset of cities is disconnected, calculating its maximum distance is unnecessary. Techniques like union find or adjacency checks can help you identify and skip disconnected subsets before performing heavier computations. This problem is often used in interviews to evaluate a candidate's grasp of advanced concepts such as graph theory, bit masking, and dynamic programming. It's important to demonstrate your ability to break the problem into smaller components and optimize effectively. Mastery of graph traversal methods like BFS and DFS is critical, as these are used both for verifying connectivity and calculating distances. Interviewers also value pre-computation strategies, such as preparing shortest path data in advance, to optimize the solution. Be ready to discuss trade-offs between brute force enumeration and more efficient approaches like bit masking or dynamic programming. Lastly, always clarify constraints and edge cases with the interviewer, such as how the solution should handle small versus large graphs or disconnected graphs. To deepen your understanding of this problem, it's helpful to explore similar problems. For instance, LeetCode 1245 focuses on finding the diameter of a tree, which is essentially the longest path within it. LeetCode 2316 deals with graph connectivity and counting unreachable node pairs, which sharpens your ability to analyze graph structures. LeetCode 1466 challenges you to adjust edge directions to ensure all paths lead to a specific city, emphasizing traversal techniques. Finally, LeetCode 133 involves cloning graphs, which tests your ability to reconstruct subgraphs, a skill relevant to handling subsets of cities in this problem. There are several approaches you can consider for solving this problem, each with its pros and cons. A brute force enumeration method involves generating all subsets of cities, checking connectivity, and calculating the maximum distance. While simple, this approach becomes highly inefficient as the number of cities increases, with a time complexity of 2 to the power of n asterisk n squared. A more optimized approach is to use bit masking alongside BFS or DFS. Bit masking efficiently represents subsets, while graph traversal ensures connectivity and leverages pre-computed distances. This works well for small graphs but remains exponential in the worst case. Dynamic programming introduces another layer of optimization by storing results for smaller subsets and building up to larger ones, reducing redundant calculations. However, it's more complex to implement. Lastly, graph compression techniques, such as merging nodes or removing redundant edges, can reduce graph size, though this adds pre-processing overhead. Each approach has its place depending on the problem constraints and input size. Great job! We've successfully tackled problem number 1617 and learned important concepts in graph theory and bit masking. Remember, practice makes perfect, so keep challenging yourself with similar problems. Don't forget to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!